or that our universe was just Euclidean. But with non-Euclidean geometries in the race now, whether or not the universe is Euclidean or not has to be proved through observation and experiment by astronomers and cosmologists, not by mathematics alone, as people had assumed for hundreds of years before, which was ludicrous to them. The other part of peer review is continuation. There's a lot of great things that came out of non-Euclidean geometry in the years that followed it, and a lot of work it inspired. But I'll focus on one application here: general relativity. One of the main players in the formulation of non-Euclidean geometry was Bernhard Riemann, of Riemann hypothesis fame. He first formulated elliptic geometry, but he also described the more general Riemannian geometry. The thing about elliptic geometry and spherical geometry is that you have positive curvature, so beefy triangles. With Euclidean geometry, you have zero curvature, exactly 180 degrees. And with hyperbolic geometry, you had less than 180 degrees, skinny triangles. With Riemannian geometry, instead of consistent curvature like the examples I just mentioned, you have all sorts of weird general curvature, which is great when you have general curved geometry like in Einstein's theory of general relativity. Riemannian geometry allows us to calculate things like how black holes warp space-time and light around them. Without it, frankly, a lot of that math would be impossible. To wrap up, I should reiterate that this process of critique and continuation carried on for several decades after Beltrami, Riemann, and the many others I didn't cover here. There was a lot of hand-wringing and philosophy and upheaval in the math community. I'll cover some of that in the next section of the video. But in short, peer review is incredibly important, even though it can take decades. We need it both for the testing of ideas, but also just because sharing those ideas can sometimes stimulate new ones. The first people to publish work on hyperbolic geometry were Lobachevsky and Bolyai, and Riemann didn't start his work on non-Euclidean geometry until after they published. If they hadn't, Riemann may never have worked on these ideas at all, and we'd be out of theory of relativity. And sometimes peer review helps convince ourselves that we're correct in the first place. After all, Alhazen and Sakari didn't think their results about non-Euclidean geometry were special at all. And yet, look at where their mathematics ended up, admittedly after many, many years of further work and critique and continuation. And consider where it might go next. Part 4. Mathematical Thinking and the Scientific Method. Now that we have this process, forming a question, experimenting, and reviewing, did anyone else notice that this seems to look like kind of a scientific method for mathematics here? It's an interesting thought, but there's a few big holes in this idea. Most important of these holes, and what I'm going to be focusing on in this section, is this. If we're running scientific experiments in mathematics, what are these things that we're experimenting on? There are a lot of possible answers to this question, and a lot of them date back to that big philosophical mix-up I alluded to earlier. The one that happened after we got non-Euclidean geometry and everybody's minds were blown. I'm not going to spend a lot of time talking about each individual philosophy. Frankly, there's a lot of ground that I could cover, and a lot of ground that I don't have time to cover. So I'm just going to skip over that entire minefield of philosophy and just go with the answer that I like, which is, to put it reductively, mathematics is a social construct. Now, I don't mean social construct in the pejorative sense. What I mean is that mathematics works best when we consider it as something that we have done together, a human activity like art and the economy and politics and science. What mathematics is these ideas that we share and teach each other and build together. We base them on our experiences of physical reality. 1 plus 1 equals 2, 2 plus 2 equals 4, based on counting and then building up from there. And we also base mathematics on what's most convenient for our minds to work with and share. We pick and choose the mathematics and sometimes the mathematical notation that we like working with. There's a side tangent here about Newton's notation versus Leibniz's notation, but that's a topic for a different video. Now, I don't think this is the objective truth of mathematics. I just think that it's a pretty useful framework for a number of reasons. One of which is that I think it's a good framework for teaching our students why mathematics is important. I'm sure many of the teachers who watch this have heard the question, but when am I going to use this in my real life? Why is this important? Who cares? I don't know if this argument works necessarily for specific things like the quadratic formula and the Pythagorean theorem. Maybe it does. But my argument is we've been working with mathematics. We've been doing mathematics together about as long as we've been doing art and science and, in some ways, money. We found 20,000-year-old bones with prime numbers carved into them, or at least tally marks with prime numbers, 2 tally marks, 3 tally marks, 5 tally marks, that sort of thing. At 20,000 years old, that's almost as old as our oldest art. Cave paintings we found that go back 40,000 to 35,000 years ago. Lascaux, the most famous cave art, arguably, is 17,000 years old, younger than this evidence of mathematics. So I say mathematics, art, and science are all societally constructed. Humans have been building ideas and techniques and styles of mathematics, art, and science for millennia. And they've been doing it by competing and collaborating and sharing these ideas throughout our culture. We collaborate to teach each other mathematics, and then we try to extend the mathematics we have to new and greater heights. We share ideas about what a triangle is, but we also share ideas about what a square number is, and what a sphere is, and what a straight line is, and what the number 2 is. We share ideas about how they work and how they interact with each other. These ideas get updated and added to and discarded all the time. The number 2 was just the second number until we invented 0, and then the negative numbers, and then all the fractions in between, and all the real numbers in between, and then the complex numbers. And now the number 2 is 1 in a humongous, an uncountable infinity of numbers. If we've been making math as early as 20,000 years ago, maybe we should sit up and pay attention. Mathematics shares a lot in common with art. We share it with each other, and old mathematics doesn't really get old in the same way that old science does, for example. Old science is stale almost as soon as it's published in some fields. Old mathematics techniques, on the other hand, they get used and revamped all the time, like old art techniques of painting and sculpture, for example. Mathematics also has a lot in common with science. We investigate problems, create new ideas and definitions to solve those problems, experiment with those ideas, compare and combine them with old ideas, and subject it all to rigorous testing and peer review. Each time we find something that doesn't work or is inconvenient to use, we try other ideas. I also think that science has a lot more in common with how we did, say, ancient mathematics with carving numbers into bones than it does with pure logic or universal truth out there in the universe. I think we were experimenting. I think that experimenting is still mainly how mathematicians do their mathematics today. And if mathematics, art, and science are also interesting that we've been doing each of them for this long, maybe mathematics is worth a second look. You may not like it anyway. I like comic books and hard rock and YouTube video essays, but I'm not a big fan of, say, romance or horror or EDM. But maybe you'll like some of it. There's a lot of mathematics out there, after all. It's a very wide field about a very wide world.